This is lesson 6, and we're going to look at the process to write a polynomial function that will approximate the functions cosine, sine, e to the x, and natural log of x. These approximations are called Taylor polynomials. In fact, we can say that the tangent line approximation is a Taylor polynomial of degree 1 that approximates some function f of x near x equals a. So if a equals 0, we learned in the introduction lesson that this was a special case, and we called those Maclaurin polynomials. Now that you know how to construct a Taylor polynomial from scratch, the following formula will be extremely important for the rest of our unit. You have to know it by heart. That definition says if f has n derivatives at x equals c, and I'm calling c the center of my polynomial, then the polynomial p sub n of x is the function value at c plus the first derivative at c times x minus c plus the second derivative at c over 2 factorial times x minus c squared, and so on and so forth, until we get to this p sub n of x. That's called the nth degree Taylor polynomial of f at c, and it's named after Brooke Taylor, who was an English mathematician. We saw in the introduction lesson that if c was centered at the origin, or c is 0, then that is called a Maclaurin polynomial, an nth degree Maclaurin polynomial for f, named after Colin Maclaurin, who was a Scottish mathematician, and we saw that in the introductory lesson, if you did that exploration with us. So now let's suppose that f is a function which has continuous derivatives, and we know that the f of 2 is 1, the f prime of 2 is negative 3, f double prime of 2 is 5, and f triple prime of 2 is negative 7. If we want to write the Taylor polynomial of degree 3 for f, and it's going to be centered at c equals 2, then we would say that f of x is approximately equal to the p sub 3 of x, which was our first definition 2 slides ago. So we want to do the f of c, or the f of 3, that's wrong, the f of 2, and then we want to do the f prime of 2 times x minus 2, and the f double prime of 2 over 2 factorial times x minus 2 squared, plus the f triple prime of 2 over 3 factorial times x minus 2. So this is that formula that showed up right here. So we're expanding that out. And that would give us the p sub 3 of x is the f of 2, which is 1, plus the f prime of 2, I don't know why I'm stuck on that 3, f prime of 2, that's negative 3, times x minus 2, plus the f double prime at 2, which is positive 5, times x minus 2 over 2 factorial, and the f triple prime of 2, which is negative 7, times x minus 2 to the third over 3 factorial. My 3 is missing right there. So this is, using that given information, we can write a Taylor polynomial centered about x minus, centered around c equals 2. Example 2, we want to use the formula above to construct a Taylor polynomial that approximates f of x equals sine of x, centered at x equals 0, and it needs to be a 5th degree Maclaurin polynomial. So we want f of x is sine, f prime of x is cosine, f double prime of x is negative sine. The third derivative is negative cosine. The fourth derivative is sine. And our fifth derivative is cosine. And just like in our exploration, we next want to evaluate the f of 0, so the sine of 0 is 0. The f prime of 0, so the cosine of 0 is 1. The f double prime of 0 is 0. The third derivative at 0 is negative 1. The fourth derivative at 0 is 0. And then finally, the fifth derivative at 0 is 1. We're writing a Maclaurin polynomial, which means our center is at 0. So our function can be approximated by a fifth degree Maclaurin polynomial if we use the f of x. So that's, this first one is 0, so we won't have a constant, but we'll have 1 times x, and then we won't have a squared term, but we'll have a cubed term, which would be negative x minus 0, so x cubed over 3 factorial. We won't have a fourth degree, but we will have a fifth degree, and that would be x to the fifth over 5 factorial. And if we continued that pattern out, I can expand that to be, we have oscillating or alternating signs, so negative 1 to the nth power, and we have x to the, it's odd power, so we're going to use 2n plus 1 power divided by 2n plus 1 factorial. So we get 1 factorial, 3 factorial, 5 factorial, and we skip all the even powers. So this is our final term for sine. Example 3, we want to write an nth degree Maclaurin polynomial for cosine, and we did that if you followed along in the exploration for this lesson. So f prime of x, f of x is going to be cosine. First derivative is negative sine. Second derivative is negative cosine. Third derivative is sine. Fourth derivative is back to cosine. And fifth derivative is negative sine. So the function value at 0 is 1. At the first derivative is 0. The second derivative is negative 1. The third derivative is 0. Our fourth derivative is 1, and our fifth derivative at 0 is 0. So our function for some nth degree polynomial, nth degree Maclaurin, is going to be 1 for a constant. Then we have no linear term, and we have a negative squared term over 2 factorial. No third degree term. We have positive x to the fourth over 4 factorial, and no fifth degree term. Our next term would be negative x to the sixth over 6 factorial, and if we continued that pattern, our nth degree polynomial would be negative 1 to the n. X and our powers are even, so 2n are even numbers, and then our factorial would be 2n quantity factorial. So this would be our nth degree Maclaurin polynomial for approximating the cosine function. example 4, these are all ones we're going to need to memorize. So write an nth degree Maclaurin polynomial for f of x equals e to the x. And f of x is e to the x. Our derivative, or our function value, is e to the 0, that's 1. Our derivative is also e to the x, and the derivative at 0 is also 1, and you see where this pattern goes. That's e to the x, and so on and so forth, and our second derivative is also 1. So our nth degree polynomial, Maclaurin polynomial, is going to be 1 for our constant, and then x over 1 factorial, and x squared over 2 factorial, and x cubed over 3 factorial, so that our nth degree Maclaurin polynomial will be x to the n over n factorial. So this is our nth degree term. And like I said, for the rest of the unit, we'll be required to memorize these polynomials, and we should be able to recognize their general form using sigma notation. So first we said that sine alternates. Sine of x alternates on odd numbers. And odd numbers can be written as 2n plus 1. So sine alternates on odd numbers, which is 2n plus 1. So our sigma notation that you want to be able to recognize would be starting n equals 0, because if we have n as 0, then our first odd number is 2 times 0 plus 1, that would be 1, up to infinity. And we're going to have negative 1 to the n power times x to the 2n plus 1 power divided by the quantity 2n plus 1 factorial. The cosine term, and cosine alternates on even numbers, so we're looking at cosine alternates on even numbers, so that pattern is 2n, and our sigma notation would be the summation from n equals 0 to infinity, negative 1 to the n, x to the 2n power, divided by the quantity 2n factorial. And then lastly, our e to the x notation. E to the x increases on the counting numbers, and the power is equal to the factorial. So that would look like the summation from n equals 0 to infinity, x to the n divided by n factorial. So these you have to be familiar with. Next, we're going to jump over to the calculator. So you might want to go grab your calculator. I'll be using the TI Inspire in my next examples. And the syntax for either calculator is as follows. If you have the TI-89, that's an older CAS calculator, or the TI Inspire, we want to be able to find the Taylor and then write the expression, the variable, the order or the degree, and then the center. And it's important to note that both of these calculators will default to a center of 0 if you don't type a center. So this is a good tool for checking your work, but all the work that's required on the AP exam will have to be written. Now here's what I've done with my calculator. Okay, let's take a look with our calculator. In the graph window, I typed in Taylor and then added parentheses, put the sine of x, comma x, and then comma 5 because example 2 was our 5th degree Maclaurin polynomial. And then I also typed in the function sine of x for example 5. We're going to use that. So in example 5, it says use the Maclaurin polynomial from example 2 and calculate the p sub 5 of 1.5. And if we come back over here to the calculator window, I can ask for the variable with the f1 function, which is my Maclaurin polynomial, and the function value at 1.5 is 1.00078125. So we've got about 1.00078125. And what's the value of the f of 1.5? So the function value, that would have been the second function, which is the sine function. And the value at 1.5 is this number, 0.997494. So it's about 0.997494. So it's really close. Now, if we want to know the error in that approximation, remember that the error was the actual value minus the Maclaurin value. So calculating the difference between those, this one minus the 1.00078125, that error is about 0.003286. On part B, we want to find the p sub 5 of 2 and the f of 2, and then calculate the error. So you want to turn the video off and do that on your own and come back and check your work with my work. I found the value at 2 is 14/15 or 0.93 repeating. The function value at 2 is about 0.9092, and the error is about 0.024. So how does the error at 2 compare to the error at 5? Well, we could say that the error at 2 is greater than the error at 1.5. What would happen if we use the polynomial to estimate the sine of 2.5? It looks like the farther away you move from the center, the greater the error will become. So I said that again here. When we use Taylor polynomial approximations, it would be good to know how accurate they are to the exact values of an infinite series. The function value estimated by the Taylor polynomial can be defined by the concept of that remainder, such as the function value is the Taylor polynomial plus the remainder, or the exact value is our approximate value plus the remainder. So by taking the absolute value of the remainder, we're calling that the error. The exact value minus the approximate value gives me the error. In order to use Taylor polynomials effectively, we will use what's called Taylor's theorem to estimate the size of the error. The remainder given in the theorem is called the Lagrange form or Lagrange form of the remainder, or Lagrange error bound. This gives us a bound for the error, not the exact value of the error. For now, let's think about the error this way. The error is the actual amount of the function minus our approximation. Let's talk about Taylor's theorem. If a function is differentiable through order n plus 1 in some interval containing our c value, then for each x in the interval, there's a number that we're going to call z between x and c, where that Taylor polynomial plus the remainder, this is the formula we're going to use for the remainder. So I'm rewriting that formula here using this m up here for the maximum to be defined as the maximum value of that next derivative, the one right after our last one. And our number z is going to be between x and c, and the bounds on the remainder found using that form are also called the Lagrange error bounds. We'll explore errors and accuracy with Taylor's theorem in the very last lesson from this unit. But for now, let's look at example 6. If you're given that the Taylor polynomial p sub 2 of x is some quadratic function, and that's the second degree Taylor polynomial for f about x equals 0. What are the signs of a, b, and c in this Taylor polynomial if the function f has the graph pictured on the right? And explain your reasoning. Well, if the f of 0 is a, then that would tell me that a is the y-intercept. And if it is represented by this graph, the y-intercept is right here, 0a, and it's a negative number, so a has to be negative. And then what else are we looking for? The b value. The b value represents the derivative at x equals 0, and that b value is the derivative is the slope of the tangent line, and our function f is a decreasing function. So f is decreasing at our c value, which is 0, and that would tell us that b has to be a negative number because the slope of our tangent line is negative. And then lastly, our c value, that c value represents the second derivative at 0 divided by 2 factorial. That's our c value. And looking at our function graph, f, it's a concave up function at 0. So because it's concave up, our second derivative at 0 has to be a positive number, which means that c would have to be a positive number. So you can look at your graph and know what each term in your Taylor polynomial represents, your second degree Taylor polynomial. And given the graph of f, you can reason through what each value has to be on that particular function f. Our last example, suppose that the function f is approximated near x equals 3 by a third degree Taylor polynomial given here. Find the values for f of 3, f prime of 3, f double prime of 3, and f triple prime of 3. Okay, so f of 3 we know would be 4. This is this value here. And the f prime of 3 would be our linear term, and we go from a constant to a quadratic term. So our f prime of 3 is 0 since we have no linear term. Next, our second derivative at 3 divided by 2 factorial would have to be this number here, negative 5, because that's our second degree term. And f double prime of 3 would have to be negative 5 times 2 factorial, which is 2 times 1. So our f second prime of 3 would have to be negative 10. And then lastly, our third derivative at 3 would be from this term. That would have to be 6, and it would be f triple prime of 3 over 3 factorial would be our term, and 6 would be the value, so the f triple prime of 3 would be 6 times 3 factorial, which is 3 times 2 times 1, so our third derivative at 3 would be 36. And then lastly, does the function f have a local maximum, a local minimum, or neither at x equals 3? And how do you know? Well, let's see. We know the first derivative is 0. F prime of 3 is 0. And what else do we know? We know the second derivative. The second derivative at 3 is negative 10, so it's less than 0. And using the second derivative test, by the second derivative test, we know that the function would have a maximum. Wait a minute, I'm writing and talking second derivative term. I said test and I wrote term. Second derivative test, the function would have a maximum at x equals 3. And just for you graphic people, we've got a concave down graph. Second derivative at 3 was negative, and the first derivative at 3 was 0. So at 3, I've got some kind of a maximum here, because the f prime of 3 is 0, and the f double prime says we're concave down through 3. And that is the end of lesson 6. Until next time.